All right, welcome. In this video, I want to continue talking about propositional logic, but in this video I'd like to take some of the logical equivalencies that we proved in the last video using truth tables and use them and show how we can use them rather to do some Boolean algebra, that is, change a Boolean expression into another one, usually a simpler one, just like we would use normal algebra to simplify mathematical functions or mathematical expressions. Here we'll use Boolean algebra to simplify Boolean expressions. So to start, I wanted to just refresh. This is sort of where we ended off last video, is with these logical equivalencies. Each one of these we could demonstrate by creating a truth table for them. And certainly if you want a little practice, that would be a good way to practice your truth tables. However, once we've proven them, we can use these as tools in our toolkit for, like I mentioned, transforming a logical expression into another one. So just as a couple examples, for instance, if we see a double negative, we can just drop the negatives. That would be a step of simplification. Or if after doing some simplification we get to, p or true, we know that that's going to simplify to just true. We can eliminate or simplify out the p. So each one of these rules is a rule. Now, most of these rules, as we mentioned, parallel some rule in algebra, in normal arithmetic algebra that we already are familiar with, hopefully. And so hopefully some of these steps that we're going to be following are going to seem pretty similar. Now, most of these ones here I think we went through last day, and then we have a couple more here, some that don't have arithmetic corresponding identities as well. Well, in this case here, some of them are going to just be fairly straightforward, like these idempotent laws. P and P is just P, that kind of makes sense. P or P is just P. DeMorgans laws, we looked at those in a little more detail last time. We actually proved them using truth tables. They're an important set of laws that actually factor into a lot of logical and set theory calculations or algebraic computation like we're going to be doing. And then we've got a couple others. Absorption is sort of another interesting one that we maybe need to jot down. A lot of these are straightforward. We probably know them already. Our internal logical computers have already internalized them. But a couple of them, DeMorgans laws, absorption, and so on, contrapositive, these are all ones that we might want to put on a little cheat sheet. But for our purposes going forward, what I want to do here is I want to do a couple examples of using these logical equivalences to prove a Boolean statement. So the first statement that I thought I might consider is this one here, not P and Q and R. This is, as an example, if we see over here, looks similar to some of these DeMorgans laws, except we now have 3 arguments instead of 2. And the question might be, or that what we might pose to ourselves is, does DeMorgans laws sort of translate or generalize if we have more than just 2 arguments? And so we might want to do this by applying, some rules. What is this statement logically equivalent to? Now, there are a couple rules that we might apply here, and I'm going to be fairly deliberate here. I'm going to leave the not out here. I can't bring the not inside because of the way that I've written it. It doesn't match any of the rules that I have already, but I can rewrite it, and I'm just going to sort of arbitrarily write it like this: P or P and Q, sorry, and R. Let's remind ourselves that all we've done here is we've used the associative property here that we can see, and we've applied it to draw brackets around that inner group. Okay, by leaving no brackets written at all here, that's something we can only do when we have an associative. We have some kind of associative operator, and is associative, or is associative, plus and multiplication are associative, meaning it doesn't matter what order that we add them or multiply them, which means that the brackets don't matter. Well, here, if the brackets don't matter, then that means we can actually add the brackets in if we want to make it appear more like one of the rules that we're going to apply. So now that it looks like this, I actually can apply DeMorgans Law. So let's maybe bring back DeMorgans Law here, in case we haven't already sort of memorized it. So what DeMorgans Law says here is we can still apply DeMorgans Law once we've treated them as two arguments here. We've sort of lumped the P and the Q together as one argument. So now, using DeMorgans Law, bringing in, I'll maybe still draw the bracket out here, we'll bring the negation in, we'll still have the P and Q. We're going to flip this sign, or flipping this sign, or that's what DeMorgans Law says. Then we have to negate the second half too, the R. Now the outer brackets, of course, we could drop, right? And now maybe we can see we can apply DeMorgans Law again to the inner term here. And actually it looks like I might run out of space, so I should write small here. We're going to get, again, not P, flip this sign, we're going to get OR, not Q, and then we still have that sign there, or not R. What we're going to see here is that indeed DeMorgans Law sort of generalizes in the sense that it the way we can apply DeMorgans Law is we can take that negation sign and we can move it inside the brackets. It then negates every term gets negated, right? But we flip all the signs too. So the ands all turn to ors. Okay, so if you have a negation of a whole bunch of ands, you can flip it to ors. Same thing, if you have a negation of a whole bunch of ors, you can flip it to a bunch of ands using DeMorgans Law. Let's do one more, because the one I actually had on the slides was slightly different. So let's take a look here. P, actually I think this is still a little different than the one I had on the slides, but it's similar in style at least. I've just increased it to 4 arguments. Does it still apply to 4 arguments? Okay, so hopefully this is true. Now, the way that I'm going to do this, now actually let's take a second, take an aside here and think a little bit about this. Now, using logical equivalent like I just did here, I did a little bit of algebra. This is just algebra here, right? Now, that means we're just modifying, we're manipulating the expression to get what we're looking for, right? To change it into a simpler form or into some form that we're hoping to transform it into. So that's not the only way we could have proven that DeMorgans Law worked on 3. We could have done a truth table, just like we did in the last video. Now, to do a truth table for this example here, we have 1, 2, 3 variables. That's going to end up with 2 to the 3, or 8 rows. Now here we have 4 variables. So again, if we have n variables, we're going to end up with 2 to the n rows. So if we had 4, 2 to the 4 is 16. So we're starting to get into the space where we might not want to do that. We might not want to fill out 16 rows of truth tables just to verify that this is, DeMorgans Law works for 4 variables. And then someone might come to us and say, well, I see that DeMorgans Law works for 4 variables, but what about 8? Does it work for 8 variables? And you might say, well, there's got to be a better way to do this than to make a table with 2 to the 8 or 256 rows. We don't, that's a lot of work. So let's see if we can just say, hey, well, can we use these logical equivalencies we've already proven and Boolean algebra to transform this into the form that we want it in? Okay, so let's try and move that negation in. Now actually, there's a couple ways to do this, but I'm not going to use the way that I sort of had on the slides. I'm going to do something different. I'm going to say, look, we've already shown an interesting thing here. If we throw brackets around 3 of them, we know that DeMorgans Law works. So why don't I do this? I'm just going to draw some brackets. I'm going to go P and Q and R like this, right? And S. So I just sort of broke off the S on the end. So I guess all I'm showing is there's more than one way, just like in most algebra, there's more than one way to transform this. Now I'm going to do DeMorgans Law because I have two terms inside. Treating everything inside this bracket as one term, I can move my negation inside. So I'll get negation on the first thing, P and Q and R. And then we're going to have to flip this sign. So we get an OR. And remember, we got the negation comes in on the second term, Q, the S. Now, if I wanted to, I could repeat all these steps up here to get me to where I want. But usually the whole point in doing algebra and the whole point in proving this equivalence here is now that I can use it. I've got it up here. I've already shown that not P and Q and R is equal to not P or not Q or not R. So probably the best thing for me to do now is just go right ahead and write the equivalent statement, not P or not Q or not R, and then not forgetting here the or not S that we bring down from above. Okay, so again showing that indeed, yes, DeMorgans Law works for 4 variables as well. So now, for instance, now that we have it, we know that it works for 2 or 3 or 4, you can maybe imagine trying to show how it could work for 5 or 6 or 7. 5 could be broken down into a pair of 3 and a pair of 2, and again with a couple steps we might be able to do that quickly. And in fact, in a couple videos down the road, we're going to encounter a technique called induction that would allow us to say, okay, well now that I've got it for 2, maybe that means I can get all of the values of n greater than or equal to 2 as well. And indeed, that is true. DeMorgans Law generalizes for any number of arguments that you might want to include. At least for the moment, we'll consider only finite number of arguments. We won't consider the infinite length expressions, as those seem a little bit strange. What does that even mean? So as we took a look, that we noticed that if we were going to use a truth table to do some of these equivalencies, we need 2 to the n rows for n variables. And so we did an example similar to this. Actually, it was slightly different than this, to show using some algebra, Boolean algebra, that indeed these statements are equivalent. And as you can see here, maybe we use 3 lines, or however you want to count this, in terms of how much effort this takes. This is less than, say, the 16 rows that we would need. And I keep mentioning this, I keep calling this Boolean algebra. And that's because the steps in Boolean algebra and some of the rules that we follow were first formalized by an English mathematician named George Boole. And so the name Boolean algebra, Boolean expression, and then also the data types that you're probably used to if you're a programmer, like Boolean or Boole, are named after George Boole. And so these, when we talk about a Boolean expression, we mean an expression of variables that can have truth values. We've been calling these propositions, and then a Boolean expression is sort of a combination of propositions combined using logical connectives like ands and ors and nots. And then we might use some of the rules of logical equivalence that we've already demonstrated with truth tables to perform Boolean algebra, which is the transformation of a Boolean expression into another equivalent Boolean expression. And we're going to spend a little bit of time in the next couple of videos sort of reflecting on what can we learn from proving certain expressions are equivalent, and what can that tell us about logic in general, and then math and computer science as well. All right, so I guess maybe I'll state the whole theorem here. A theorem is something that we want to prove. Again, I'll talk a little bit more about that in a future video. We're just getting the foundations of proofs down before we want to actually start writing a formal proof. But here, showing that something is logically equivalent is a proof. We're going to give a proof that these are logically equivalent. So here I might say this is a theorem, and we might say this is what I'm trying to prove. Okay, so how am I going to do that? Well, we're going to use algebra. Algebra is how we prove a lot of things in math, or how we have proved a lot of things in math. So now I might want to prove this. How do I prove it? Well, like most things in algebra, I'm going to start with the left-hand side. I'm going to try and get to the right-hand side. So let me just rewrite the left-hand side again. And now, as we go through steps here, we want to apply rules of logical equivalence. We will only want to show or do steps that are logically equivalent. Now here, there's a couple steps that might come to mind, and it's really up to you. I'm not certain which one you think is going to be the one that is the most fruitful. Indeed, a lot of times we are going to have to perform more than one step, and we might have to perform them. We might not have to perform them in a specific order. We might do step A and then B, or B and then A, and those get us to the same spot. So it doesn't really matter. So usually I'll say, whichever feels most comfortable for you, that's the way that you should go. And for me, we've already been doing this we've been practicing DeMorgans. DeMorgans is often the first tool I pull out of my toolkit. I don't know why. It might not be the best one. It might just be my favorite one. It might be the favorite one. So I see this negation out here outside this brackets with an and or an or in there, and immediately my brain's saying DeMorgans Law. However, some of you might also say, hey, look, there's the opportunity for us to do distribution in here. I could distribute that P in there. And it's for those of you who maybe distribution feels more natural, because that's a little bit more arithmetic way of thinking than DeMorgans. You might see, hey, we're gonna end up with a P or not P here, and that's interesting. A P or not P. Which one was that? Well, let's wait. That's getting ahead of ourselves. But keeping in our mind here that as we're building up our intuition for Boolean algebra, it's just like our intuition for normal algebra. We can maybe see a step or two ahead and say, hey, I want these things to cancel out, or I want this to, I want to drop this out later. How can I get it out of the bracket, or how can I move this into the bracket? Something like that. We can anticipate our future steps, what we want to do, and so we can make steps ahead of time to make those future steps maybe possible or more fruitful. Like I said, I'm going to start with DeMorgans. So that means I'm just going to bring the not inside. So I'm going to go not P. Remember, we need to flip this sign with DeMorgans. So it was an or, it's now an and. And then we have to negate the other term here, which was already in brackets. So I'll be careful to write it down here. Not P and Q. Okay. So again, we could, we sort of frustrated our distribution here. Distribution didn't work when we had a negation out front here. I mean, there's probably a rule that we could make up and prove where you could distribute into a negation here, but probably the best thing for us to do is apply DeMorgans again to move that negation back inside again. So what do we have here? We have not P, and now I'm going to move my not. I've got the brackets still, because I'm going to end up flipping this sign. It's going to be an or, and so ands and ors, the brackets matter. If we have all ands or all ors, then we can drop the brackets and pretend they're not there. But in this case, we need it. So the not's going to come in. We get not P. I'm doing sort of two steps at once here, and just saying not P is P. Now, hopefully, all of us, that's a very very quick step to do. That's doing like a minus in algebra. Hopefully we can do that all in one step. And then we get the not Q, but remember, we're flipping our sign. We're flipping it to an or, not Q. Okay, so we did DeMorgans Law properly. We've transferred down here. Now, because we've got this set up here with a and then an or on the inside of the brackets. Again, remember, if this was and, we just drop the brackets. If this was or, we just drop the brackets, okay? And in this case, because we have P's over here, when I say just drop the brackets, it's probably because the next step we'd want to do is lump these two together so we can get them canceling out in some interesting way, okay? But we don't have or and. We have and or, which means the only rule that we have available really is distribution. Now let's see what the distribution is going to be. We're going to get The way I like to remember it is, at least when it's written like this, I've got my singleton out here, and then we've got the pair out here. So it's the singleton, and then whatever sign this is an and then the first one, then whatever sign this is, or, and then the same thing again, the singleton, this sign here, and then the second one, not Q. Oops, wrote that slightly backwards. Okay, now, again, let's make sure we did this right. So we got P and the first term, and, sorry, not P and the first term, that's what we got. Not P and the second term, not P and the second term. How are they joined together? With this sign, or. Okay, that's distribution. If you need to go look it up on your, cheat sheet or on the list of equivalencies, go look it up. Okay, otherwise I sort of remember how it works so that I can, if they start switching it up on me, like putting a not P here or an R or something else here, I remember the pattern so that I can perform it again. All right, so what's the next rule that we're going to want to do? Now, looking at this term, I don't know how to, there's no rule I know how to simplify that, but this, what do we got here? We have not P and P. Now remember, this is what we call the contradiction. And I can't remember what we called the rule for this, but this simplifies to false. Okay, P and not P. If one of these is true, the other one is false, so the whole thing must be false. Okay, or keep it going, not P and, oops, not Q. Okay, this part again, I don't know how to simplify, but let's see this bit. False. Now remember, false has got to do something here. Either, in this case, false or. What happens when we take a false and we or it to something? Nothing. This stuff still has to happen. Whatever this is the output. If this the whole thing is true, the whole thing is true. If the whole thing is false, the whole thing is false. So we can just drop the false off. So technically, we can get to not P and not Q. Now, if this was an and, the false would dominate the whole thing and force everything to be false, right? Which would mean the whole thing we started with was a contradiction. If we start at the beginning with a statement and we simplify, and at the bottom we get just false, F, that means the whole thing we started with was false. So it must be a contradiction, always a contradiction. Same thing, if we go all the way down, all the way down, all the way down, and we get true, then we must have a tautology, something that's always true. Okay, but we went down, simplify, and we got this. Can we simplify this further? Not really. Well, some people might think that this is more simple. Okay, doing DeMorgans backwards to pull the not out, factoring the not out. Some people like this form. Some people like this form. I kind of like this form, but that's just my own bias, right? Other people will like this form out here, but these are the same. These are probably the simplest we're going to be able to get. And this was what we were trying to prove. Remember, this was what we were looking for. So we got where we were trying to go, and usually that's when you stop. Okay, you do your algebra until you simplify as far as you feel like you can simplify, or you get to some target you were aiming at. Okay, so once again, this technique that we've been using here or applying here is called Boolean Algebra. It's very similar to algebraic algebra, where we just sort of apply simple rules. A couple difference, of course, there are a few bonus rules like absorption and DeMorgans laws that are new for logical connectives. What else? We've changed up our equal symbol. We use 3 bars, which means equivalence, logical equivalence, not equals. So this is a little change, but otherwise the techniques are very similar to the arithmetic techniques that you've already used. So I do recommend practicing a little bit. Probably the easiest way to do it is just build some sort of logical statement and see what it is equal to. Now, we've been mostly using nots, ands, and ors, and there's a reason for that. I'll get to that in a future video. But remember, we could also use if and only ifs, ifs. There's XORs in there. There's other connectives too. So go ahead and build up a sentence, P XOR Q, if and only if R, what is that equivalent to? See if you can simplify it down, maybe eliminating out some of your symbols so that you can write it only using some simple symbols. That might be a way to go. Okay, so I leave that as some practice. And in the next video, I think I'm going to start talking about set theory. All right, well, thanks a lot for watching, and we'll see you in the next video.